apply what we've been learning about kinematics to the situation of freely falling objects. Now, a freely falling object is an object that moves under the influence of gravity alone, regardless of its initial motion. So a freely falling object could be an object that you drop, it could be an object that's thrown, it could be launched at an angle. Those are all situations where once you let go of the object, the only force acting on it is gravity. We'll talk about gravity forces later on. Now, all freely falling objects near the Earth's surface undergo the same acceleration. Now, when we were talking about cars accelerating in the previous examples, that acceleration is caused by the friction of the tires against the road, which ultimately is produced by the engine of the car. Now, this acceleration is coming from the gravity force between the object and the Earth. And it turns out that when you're near the surface of the Earth, every object, no matter how big or small it is, experiences the same acceleration. This acceleration is a vector. Acceleration is always a vector. It has a magnitude of 9.8 meters per second squared, and it has a direction pointing down. The word down means toward the center of the Earth, in the radial direction towards the Earth's center. Now, students often get confused about signs with the acceleration of gravity. Remember, signs just depend on what coordinate system you have chosen. In physics, there's no such thing as an intrinsically positive or negative number. Positive and negative refer to a direction. So it's usually the case that we define a coordinate system that looks something like this. We'll say that we have an axis pointing up. Oftentimes we'll call that the y-axis, and that up direction is considered positive, and we'll have a horizontal axis, maybe two horizontal axes, and like pointing to the right would be positive along that horizontal axis. So if we decide that up is the positive direction, then the acceleration due to gravity is 9.8 meters per second squared down, or that minus sign indicates down in the opposite of the up direction. Sometimes we'll encounter a coordinate system where the down direction is considered positive. When that's the case, then acceleration vector would be positive 9.8 meters per second squared. Again, just to emphasize this point, this minus sign or lack of a minus sign is just telling you what coordinate system you've chosen. Gravity always accelerates you downward, and whether you want to call that positive or negative depends on your choice of coordinate system. Okay. At this point, you just have to believe that gravity causes a downward acceleration with magnitude 9.8 meters per second squared. Later on, the semester, we'll learn where this comes from. We'll be able to derive that number using Newton's laws and Newton's law of universal gravitation. So stay tuned for that. That's several weeks away, but we'll learn where this comes from. For now, just take it as a fact that gravity causes you to accelerate at this rate. So, because this acceleration is a constant number, that means that kinematics applies, and everything that we learned in the last video is still true. So we can analyze problems involving objects falling using our same kinematics process. So let's do several examples now. let's say that we drop an object from a height of 2 meters. So 2 meters is about this high. Say we drop it, it hits the ground. We'll answer a few questions about this motion. So let's ask how long, question A, how long does it take to hit the ground? And question B, what is its velocity right as it's striking the ground, right before it strikes the ground? Okay, so let's use our kinematics process to answer these questions. Question A, how long does it take for this object to hit the ground after you drop it? Well, first step in the process, identify that it's a kinematics problem. It is, I'm telling you that. Step 2, identify known quantities. Okay. So, what do we know? Well, we know that the initial position is 2 meters above the ground. And a lot of times when we're dealing with vertical motion, it's just kind of traditional to use y as your variable instead of x. So I'm going to use y, but these kinematic equations are exactly the same. Just replace all the x's with y's. It doesn't matter. So here are our known quantities. We know the initial position is 2 meters. We know the object's hitting the ground, so the final position, y final, is 0 meters. We know the acceleration is minus 9.8 meters per second squared, keeping in mind that this assumes that we've defined a coordinate system where up is positive. If up is positive, then we say that A is negative, meaning down. Now, we do know one more thing. We know that from this word drop. So, when I drop an object, I let it go from rest. It has an initial velocity of 0. That's different from throwing an object up or throwing an object down. Drop implies v initial equals 0. So again, sometimes when you read these problems, it's not going to outright say the values of certain things. This problem didn't say y final equals 0, v initial equals 0. It said it hits the ground, so we can assume that the final position is 0. And it said drop, so we can assume that the initial velocity was 0. All right, our unknown quantity. How long does it take? That unknown quantity is t, the time. So we've identified our unknown, and now we need to select the appropriate equation. So let's choose the right equation to use. Okay, first equation, that doesn't help And I should point out why, actually, because sometimes people get confused about this. When the object strikes the ground, the final velocity we're talking about is the velocity it has right at that instant before it hits the ground and stops. So we don't actually know v final. Sometimes students get confused and think v final is 0 because it hits the ground and stops. That's a collision process that's happening at the end. So we're considering that final velocity to be right before the object collides with the ground. And as of now, we don't know what that final velocity is. So we can't use equation 1 because it has too many unknowns. Equation 2, we can't use that either for the same reason, too many unknowns. Equation 3, this looks pretty good. So, yeah, and equation 4 we can't use either because we don't know v final. So equation 3 is the one we want to use, and again, I'll just replace the x's with y's. We're trying to solve for t. Notice that in this problem, v initial is 0, so this term goes away. It becomes 0. And we can say 1/2 at squared equals y final minus y initial, or t equals 2 y final minus y initial over a square root. Y final is 0, y initial is 2 meters, a is negative 9.8. When you put in all those numbers, you get 0.639 seconds. That sounds reasonable. When I drop this pen from 2 meters, it takes a little bit less than a second for it to hit the ground. So let's do part B. I'll have to erase this. All right, part B. What's the velocity of that object right before it strikes the ground? Remember, not after it hits the ground and stops, but at the split second right before it hits. So we still know that v initial is 0, y initial is 2 meters, y final is 0, a is negative 9.8 meters per second squared. We can use our result from part A, that the time is 0.639 seconds. And we want to find v final. Now, we've got a lot of options. It looks like the first equation will work. It looks like the second equation will work. It looks like the third equation will work, and the fourth equation. We have so much information that we could choose any of these to solve the problem. I think that's right. So let's make our lives easiest and choose the simplest one of those, which would be the first one. V final equals V initial plus AT. V initial is 0, A is negative 9.8 meters per second squared. T was 0.639 seconds. So our velocity is negative 6.26 meters per second. And again, that negative sign means that the object is moving downward because we considered up to be positive. All right, next example. Things are going to get pretty serious in this next one. I think this is going to be the first problem where you'll have a Welcome to Physics 6 experience. This is our first genuinely challenging problem. Okay, here's the situation. Let's say you're standing on the edge of a building. This building is 50 meters high. And you throw a ball up. I kind of ran out of room on this board, but imagine that you can throw it higher than that. You throw this ball straight up, so it goes up, comes back down, lands on the ground 50 meters below where you threw it from. We're going to answer several questions about this situation. We'll do 4 questions. Because I don't have a whole lot of room on this board, I'll just write them one at a time, solve each of them, erase them, and do the next. So, first question. How long does it take for the ball to reach its peak height? So when you throw this ball, it goes up for a while. Gravity's pulling it down the whole time. Eventually it can't rise any higher, and it reaches at peak height before it continues falling. So you throw your object up, it reaches some peak height up here, and then its velocity goes down. You can think of the velocity vector, by the way. When you first throw it, the velocity vector is pointing up. It's slowing down, reaches the peak, and then the velocity vector flips direction, and now that velocity is pointing down. Acceleration vector, by the way, is pointing down the whole time because this is Earth's gravity. So during this motion, here's what's happening with velocity and acceleration vectors. Here's my acceleration, always down. When I throw the ball, velocity is up. These two vectors are in opposite directions, so the ball is slowing down. And then it reaches the peak. Velocity vector is momentarily 0 at the peak. The ball essentially stops at the peak. And now, velocity points down, and it speeds up because velocity and acceleration are pointing in the same direction when the ball is moving down. All right, so how long does it take for the ball to reach its peak height? We'll do our process. Identify that this is a kinematics problem. It is, I'm telling you that. Identify known quantities. Okay, there are a few things that are specifically stated and a few things we have to infer. What's stated is that the initial position is 50 meters and the initial velocity is 15 meters per second. What's not stated, but which is always true on the Earth's surface, is that the acceleration due to gravity is 9.8 meters per second squared, pointing downward. That means down. And the other thing that's not stated, but which is definitely true, is that the velocity at that peak height is 0. Whenever you throw an object up at the peak of its motion, that velocity is 0. Now I want to point out another thing about these quantities that I've mentioned a few times already, and that's what I mean by initial and final. I'm labeling these initial and final, but keep in mind that initial and final depend on what question you're answering. For this question, my initial situation is when the ball is first thrown. The final situation is when the ball reaches its maximum height. I'm not considering the final situation to be when the ball hits the ground. In some other parts of this problem, that will be the final situation, and you'll have to adjust your thinking for final to mean when the ball hits the ground. But right now, final means at the peak height. All right. What's our unknown? Unknown is how long it takes, the time. So which equation should we use? Well, we know several things, but we just want to solve for t, so let's use the easiest tool for the job. Actually, there's only one tool that we can possibly use. That's the first equation. So we'll use VF equals VI plus AT, and we'll solve it. AT equals VF minus VI, T equals VF minus VI over A, which is 0 minus 15 meters per second over minus 9.8 meters per second squared, which gives you 1.53 seconds. All right, so after 1.53 seconds, the ball is at its highest point. Let's move on to the next question I want to ask in this problem. Part B. What is the maximum height that the ball achieves? We'll keep using our process. Here's what we know. The initial, 15 meters per second. V final, 0 meters per second at the peak of that motion. A, minus 9.8 meters per second squared. Y initial, 50 meters. T, 1.53 seconds to reach that peak height. Unknown. Y final. What is the final height at that maximum? Let's use the right tool for the job. Let's pick a good equation to use here. We have a few options. Second or third equations will work. Let's just use the second one. Y final equals Y initial plus 1/2 V initial plus V final times T. Plug in these numbers. So solve. 50 meters plus 1/2, 15 meters per second plus 0, 1.53 seconds, and that gives us a maximum height of 61.5 meters. So the ball goes 11.5 meters higher than it started from. So I didn't draw this picture to scale because I ran out of room, but it goes up 11 meters before it turns around and starts falling down. All right, let's keep going. These questions are going to get harder. Part C is the hardest one. You can pause the video and take a break now if you need. For some caffeine. Okay, part C. This is the evil question. How long does it take for the ball to hit the ground? It doesn't sound so evil when I ask it, but it is pretty evil. Let's do our process. Here's what we know. Keep in mind that now the final situation is the ball hitting the ground. For parts A and B, final situation was when the ball was at the maximum height. Now, the final situation is when the ball reaches the ground. So adjust your thinking for what these labels, initial and final, mean now. Initial's the same. Initial is still when you throw it off the building. All right, so we still know V initial. We still know Y initial is 50 meters. Now Y final is 0 meters. The ball's hitting the ground. And A is still negative 9.8 meters per second squared. Those are the 4 quantities that we know. That's what we know. We don't yet know how long it takes to hit the ground. We don't yet know what the velocity is when it hits the ground. So unknown, what we're solving for in this problem is t. So let's select the appropriate equation to use. First equation doesn't work because we don't know v final. Second equation doesn't work, again, because we don't know v final. Third equation, yes, that's the one. Fourth equation doesn't even have t in it, so it's completely useless. So third equation. Now, this equation is a quadratic equation for t. We used this equation for an earlier example, and we were able to avoid having to use the quadratic formula because the one time we used it before, we were able to cross out this v initial term. We can't cross that out anymore. We've got to use the quadratic formula to solve for t. So it's going to take some algebra to get this in the right form. So see if you can follow along with me. I'm going to rewrite this. So here's our process for solving. I'm going to rewrite this equation, 1/2 at squared plus v initial t plus y initial minus y final equals 0. So I wrote things in a different order, and I moved y final to the other side of the equation. So this thing looks like it's in the format a t squared plus bt plus c equals 0. And hopefully you recognize that as being a quadratic equation where the solution is minus b plus or minus square root b squared minus 4ac all over 2 times a. But what I mean by this capital A is 1/2 times acceleration. What I mean by capital B is v initial. And what I mean by c is y initial minus y final. So this really is negative v initial, negative v initial plus or minus v initial squared minus 4 times 1/2 little a times y initial minus y final, whole thing divided by 2 times 1/2 a. Now there is your general answer. When you throw objects from some initial height and they land at some final height, this is how long it takes. So we got to plug in all the values in here, and you can do that on your own. Remember, when you use the quadratic formula, it gives you 2 solutions. You take the plus root and the minus root. So our 2 solutions are negative 2.01 seconds and 5.07 seconds. Now we have to think about these and decide if they make sense. Negative 2.01 seconds would mean the ball hits the ground 2.01 seconds before you threw it. That doesn't make any physical sense. So we throw away that answer. 5.07 seconds means the ball hits the ground 5.07 seconds after you throw it. So that answer makes sense. So when you use the quadratic formula, you got to make sure your answers do make sense. That -1 doesn't make any sense. Okay, so I went through this algebra maybe kind of fast, so I recommend when you're studying at home, pause the video, see if you can derive this. Make sure you're able to plug all these numbers into this formula and get these answers. A lot of students struggle with being able to use their calculators and actually computing this thing. So make sure you practice doing that so that you can get the right answers out. Now we're not done yet. I'm going to ask one more question about the situation. This last question is easy. Part C was the hard one. Last question. What is the ball's velocity when it hits the ground? Keep in mind that this is how people talk in physics. What's the ball's velocity when it hits the ground? Now, obviously, after the ball has hit the ground, it stops. But we're not asking like after it's collided. We're saying, what's the velocity like right at that instant before it strikes the ground? We'll do our process. Here's what we know. Y initial, 50 meters. Y final, 0 meters. V initial, 15 meters per second. A, negative 9.8 meters per second squared. We know the time to hit the ground, because we just figured that out on part C, 5.07 seconds. Unknown. V final. Let's select the right equation to use. There are a couple different ones we could use. I think first one is the simplest. We won't have to do any algebra. V final equals V initial plus AT. Super easy. 15 meters per second plus negative 9.8 meters per second squared times 5.07 seconds. That gives you negative 34.7 meters per second. And I just want to point out that there's a negative sign there. That negative sign makes sense because when the ball is about to hit the ground, it's traveling downward. And in our coordinate system, we assumed that up was positive. So we threw the ball with positive upward velocity to start with. Gravity took over. And caused that ball to fall downward. It flipped the sign of its velocity vector so that as it's moving down, its velocity is negative. All right, so now you've seen how we can analyze freely falling objects, like that pen I just dropped, using kinematics. This situation of throwing a ball off a cliff or off of a building is pretty involved. So now you've gotten your first taste of some pretty difficult physics problems in this lecture.